Hello everyone, welcome to my YouTube channel. Thank you so much for your amazing response, awesome feedback, and valuable comments. I'm making so many quantum computing related podcasts and educational material as well as job related information, certification related information. And I'm very happy that you have given me excellent feedback, awesome response. Taking those important pointers into consideration, I have decided to make entire quantum computing course in 100 classes, as I got so many requests from international and national students, and continuously I got messages that sir, why don't you make entire quantum computing related learning series. So I am making this series from today onwards, and I have prepared a very good, easily understandable material, and also I have framed a syllabus for quantum computing, which will be very useful for your jobs and further research, as well as whatever you try to accomplish in your career. This particular syllabus and the content that I am going to deliver will be very useful for your future learning. And mostly this particular course will be completed in 100 classes, as I already claimed. And the other important thing I want to tell you is that in this entire material I have framed taking several books into consideration, internet sources into consideration. It is not one source material, it has many ingredients. And I'm starting this particular course with quantum mechanics fundamentals. As you know, quantum computing has so many concepts related to quantum mechanics, physics, mathematics, computer science. So I'm trying to cover everything in this 100 lessons in a most easiest manner, so that every student, whoever listens to this course, will understand it in a technical manner. Apart from this, I request you all to listen this content from beginning to ending, and do provide your valuable comments so that I can improve my delivery of content, and also whatever you ask questions will be answered in the video form in the coming days of our learning. So thank you so much for giving me this opportunity. Do like this particular course, and also do share it with your friends, and please provide your valuable comments. So let us jump into this quantum computing course with fundamentals of quantum mechanics. So I started with course objectives and course outcomes for fundamentals of quantum mechanics. So you will be understanding wave particle duality and uncertainty. You will learn postulates and math of quantum mechanics or basic quantum potential problems, apply matrix methods in quantum theory, study angular momentum and hydrogen atom. And whatever the outcomes you are going to get after this completion of fundamentals of quantum mechanics are framed here. You will be describing quantum concepts like matter waves, use Schrodinger equation and operators, analyze quantum systems with simple potentials, apply matrix formalism and Dirac notation, solve angular momentum and hydrogen atom problems. So this is what you are going to learn in this particular time of time frame of video that I'm going to deliver today. And also further classes, I will tell you where I'm going to end fundamentals of quantum mechanics as a future course of action. So coming back to our discussion, I am Dr. K.V.N.Rajesh. I am a IBM quantum certified professional. I have so many other credentials, but I want to mainly focus here about my IBM quantum learning. I have done certifications in this area as a part of learning quantum computing. So coming to the discussion, so let me give you some pointers. The slide will be static for a while. So here, if you observe carefully, there is a question: is light a wave or is it a particle? For more than 200 years, physics argued about this question. You all know that, right? And the surprising answer given by quantum mechanics is light is both. Even more shocking matter itself behaves like a wave. Okay, today we will understand this revolutionary idea known as wave particle duality, which lies at the foundation of quantum mechanics. So if you see, everything you see in this world is all like for example, your phone, your hands, even your body, right? what I told you, none of this is truly solid, but they appear to be solid. That is what, like your phone, your hands, your body, right? They all are appearing to be solid, but they are not truly solid. At the deepest level of reality, nature is playing a strange game. Sometimes it behaves like a wave, sometimes it behaves like a particle, and sometimes it behaves like both. This is not philosophy, this is not imagination, this is real physics. So we already saw that electrons behave like waves, they diffract, they interfere, they create patterns just like ripples on water. But here's the shocking part, the same electron under a different experiment behaves like a tiny particle. So what is it really? Is it a wave or is it a particle? So the answer will change the way you understand the reality forever. The strange behavior is called wave-particle duality. So today I'm going to discuss about wave-particle duality, and once you understand this idea, you will realize something unbelievable. So nature does not care how we want it to behave. It behaves differently depending on how we observe it. So in this video, we are entering to the heart of quantum mechanics, a world where classical rules break, logic feels uncomfortable, and reality becomes beautifully weird. So stay till the end. This is the moment when certainty disappears and probability takes over. So I want to enter into the next slide and let you know about the legacy of Max Planck. See, before Max Planck, physicists believed they had already understood light. Light, they said, is a wave, and the evidence seemed clear. Light bends around corners, light spreads out after passing through a narrow gap, light creates beautiful interference patterns. These are the things that only waves can do. For example, when light passes through a single slit, it doesn't travel straight like tiny bullets. Instead, it spreads out. So this is called as diffraction. And diffraction was strong proof that light is a wave. So for decades, the scientific world felt confident light is a wave. Case is closed. But then came a problem. A problem so serious that classical physics could not explain it. When scientists studied hot objects glowing like heated metal, the math completely failed. The predictions were wrong. Reality refused to follow the equations. That's when Max Planck made a bold and uncomfortable decision. He suggested that light does not release energy smoothly like a wave. Instead, it releases energy in tiny packets, discrete packets, individual chunks. He called them quanta. Okay? That single idea changed everything. Without realizing it, Max Planck had cracked open the door to quantum physics. He showed us that even something as familiar as light does not behave the way we expect. Light is a wave, but also it behaves like particles. And once the door has opened, there was no turning back. Einstein walked through it. Bohr followed. De Broglie pushed it further. And today, every quantum idea we study traces its roots back to this moment. So when we talk about the legacy of Max Planck, we are not just talking about one equation. We are talking about the moment when physics accepted a shocking truth that nature is not continuous, reality is quantized. And that realization changed our understanding of the universe forever. Now I will show you one picture, right? So here, if you see this picture, in this picture, you closely look at this picture. On the left side, you see straight lines, right? If you see the left side of the picture, right, they are straight lines, they are evenly spaced lines. So this represents light traveling as a perfect wave, moving forward in a parallel, right? If light behaved like tiny particles, this is exactly what we would expect. Straight paths, no spreading, no bending. But something interesting happens at the center. The light reaches a narrow opening, single slit. And the moment light passes through that slit, everything changes. Instead of continuing straight, the waves spread out. They bend. You can see in the picture. They curve. They fan out in all directions. This spreading is called as diffraction. When you see on the right side of the image is not randomness. It is wave behavior in its purest form. So every curved line represents a wavefront emerging from the slit. So the slit itself becomes a new source of waves. This is something particles simply cannot do. If light were only made of particles, it would pass straight through the slit and form a narrow bright line. But instead, light fills the space. It bends around edges. It interferes with itself. It behaves exactly like a wave. This single experiment was one of the strongest proofs that light has a wave nature. And for a long time, physicists believed this settled the debate. Light is a wave, end of the story. But we will soon discover nature had a surprise waiting, because light does all of this, and yet under other conditions it behaves like a particle. And that contradiction is where quantum physics truly becomes. Now, let us go to the next slide. If you see, diffraction at a slit. So, let us carefully look at this slide. What you are seeing is called as diffraction at a slit. First, focus on the bright red pattern in the image. This pattern is produced when laser light passes through a very narrow slit. Now, here is the most important point in this slide. Only waves behave like this. Okay? What is actually happening? When light passes through a wide opening, it mostly travels straight. But when light passes through a very narrow slit, something surprising happens. Instead of moving straight ahead, the light spreads out. This spreading of light is called as diffraction. Why this is important? Diffraction is a pure wave phenomenon. Particles do not spread out like this. If light were made only of particles, you would expect a sharp shadow behind the slit. But instead we see a pattern, a bright central region, followed by alternating bright and dark regions on both sides. So this pattern proves that light behaves like a wave. So what is the pattern? The bright regions occur where waves reinforce each other. The dark regions occur where waves cancel each other. This process is called as interference. So this single image which I am showing you actually shows two wave effects together. One is diffraction, the other one is interference. This is why this particular image is going to tell that only waves behave like this. So now let us discuss about interference. So what is interference? Before getting into interference, there is one concept called as connection to wave particle duality. So before quantum mechanics, experiments like this convinced scientists that light is a wave, but later experiments showed that light also behaves like a particle, right? So whatever I have shown in the previous slide, that tells only one side of the story, the wave nature of light. To fully understand light, we must accept both wave and particle behavior. This dual behavior is called as wave particle duality. Okay. So to simply remember, if light spreads out and forms patterns, that is wave behavior. If light transfers energy in packets, that is a particle behavior. Both are real, both are necessary. So before this slide, this interference slide, I told you about diffraction. The diffraction pattern is just not a picture which I have shown to you. It is evidence. Evidence that nature does not follow simple rules. At very simple scales, nature behaves like a particle as well as wave at the same time. Right? Now, interference. What is interference? That is the next idea. Look at the two waves shown on this slide. One wave is down in red. The other wave is, see, one wave is drawn in red, if you see, and the other wave is drawn in blue. So these are the two separate waves moving through the same region. What does interference mean? When two waves meet each other, they do not bounce off like solid objects. Instead, they overlap. This overlapping of waves is called as interference. Interference simply means waves adding together. So let us take a case, right? If the crest of one wave meets the crest of another wave, they add together, the result is a bigger wave. This is called as constructive interference. In terms of light, this produces a bright region. So there is another concept called as destructive interference. That is the opposite situation. If the crest of one wave meets the trough of another wave, they cancel each out. The result is no wave at all. That is called as destructive interference. In terms of light, that produces a dark region. So this behavior is unique to waves. Particles do not cancel or reinforce each other like this. So whenever we observe reinforcement, cancellation, bright and dark patterns, we immediately know that wave behavior is involved. Please note this point. So how do we connect this interference to diffraction? That is the reason why beginning of this interference slide, I spoke about diffraction once again, right? So diffraction patterns contain alternating bright and dark regions. If you see the previous image, and diffraction spreads the wave and interference creates the pattern. Both effects together prove the wave nature of light, right? So interference is one of the strongest proofs that light behaves like a wave. Later we will see that electrons also show interference. That is when we realize something amazing. Even matter behaves like a wave. Okay, so this is one of the key ideas behind wave-particle duality. So you can remember interference like this. Waves can add together. That is nothing but brightness. Cancel out. That is nothing but darkness. Only wave does this. So this simple picture of two waves is not just a diagram. Evidence that nature works in waves at very small scales, and this is exactly why quantum mechanics was born. Now let us go to one of the important, this is also a slide which tells about like waves interference with each other, and they can reinforce each other or cancel each other out. So as I told, we are going to discuss about the most important experiment, that is Young's double slit experiment. Right? This is the most important experiments in physics. Single experiment clearly shows that light behaves like a wave. So in step 1, if you see light approaching the slits, at the top of the diagram, if you see, there is a coherent light falling on a barrier. Coherent means the light waves have the same frequency and move together in step. So the arrow shows the direction of light propagation. The light now reaches a barrier that has two very narrow slits. So if you see in step 2, I'm categorizing the entire diagram into step 1 and step 2. In step 2, light after the slits, if you see, when light passes through each slit, it does not travel straight. Instead, it spreads out. Each slit now acts like a new source of waves. So now we have two waves spreading out from the two slits, right? If you see in step 3, overlapping of waves is there. As these waves move forward, they begin to overlap. This overlapping causes interference, which I have discussed in the previous slide. At the same point, the waves add together. At other points, they cancel out each other. That's what I told previously. In step 4, if you see, there is a constructive interference. See, look at the regions marked in the diagram, right? That is what is constructive interference. Here the crest of one wave meets the crest of another wave. The result is a stronger wave, right? These regions appear as bright bands, if you see, right? And if you observe, there is destructive interference. Now look at the regions marked destructive interference in the diagram. Here the crest of one wave meets the trough of another wave. So they cancel out each other on the screen. These regions appear as dark bands. Okay. So if you see, there is a pattern on the screen at the bottom. That is nothing but the intensity distribution of fringes. So this is a series of bright regions, dark regions, bright regions again. So this pattern is called an interference pattern. Why this is so important? This pattern is possible only if light behaves like a wave. The lights were only made of particles, we would see just two bright spots. But instead, we see many bright and dark bands. So this proves the wave nature of light. So how do we connect this diagram with wave-particle duality? So later experiments showed that light also behaves like a particle, and even more amazingly, electrons also produce this same pattern. This means both light and matter exhibit wave behavior. So this dual behavior is called wave-particle duality. So once again, I am telling you, if you want to simply remember, two slits, two waves, interference, and interference means bright and dark bands. Only waves do this. So Young's double slit experiment is not just an experiment, it's a message from nature. At very small scales, nature does not behave like particles or waves alone, it behaves like both. And that is where quantum mechanics begins. Right? After Planck, now let us understand what happened after Planck's discovery. So that is what I am going to show you in the next slide. See, here if you see, there is an important observation from Max Planck that he found everything, something very surprising. He discovered that under certain conditions, light does not behave like a wave. Instead, it behaves like a stream of tiny particles. So these particles are called as photons. Right? What are photons? Photons are not imaginary ideas. They are the real particles. They are just as real as electrons. So each photon carries a simple fixed amount of energy. That energy depends on the frequency of light. So there are two natures of light. Right? So here we have a problem. Earlier experiments showed that light behaves like a wave. Planck's discovery showed that light behaves like a particle. Which one is correct? The answer is both. Right? So both are real. The wave nature of light is real. The particle nature of light is also real. Something which is little bit confusing, but you have to see the reality. Light is not sometimes wave and sometimes particle. Both behaviors exist together. Why do we need both the ideas? Some experiments can be explained only by wave theory. Some experiments can be explained only by particle theory. To explain the behavior of light in a fully easy manner, we must use both the ideas. So this strange but beautiful behavior is called wave-particle duality. Light behaves like a wave and also like a particle. So what is the strong takeaway? Light does not choose to be wave or a particle. Nature chooses what we observe, and the choice depends on how we perform the experiment. So how can we connect to this quantum mechanics? The idea completely changed physics. Whatever the idea I am telling you, it completely changed the physics. It showed that classical thinking is not enough. And this is the doorway of quantum mechanics. Now let me explain you about de Broglie. So when it comes to de Broglie, there is one story. There is a question asked by de Broglie after Planck. De Broglie showed that light, which was thought to be a wave, can be like particle also. De Broglie asked one question. He said, if waves like light can behave like particles, then why not the other way around? So the big question, is it possible that tiny particles like electrons could also show wave behavior? So even bigger question is, and if electrons behave like waves, could they have a wavelength just like light waves? So why this question was shocking? You all should know during that time. Until then, electrons were thought to be small solid particles. No one imagined that something with mass could behave like a wave. So de Broglie completely changed this thinking. And his radical idea was the most important idea during that time. De Broglie proposed that every moving particle has an associated wave. So that wave is called a matter wave. Right? So electrons are not just particles. They also behave. They also have properties. They can interfere. They can diffract exactly like light. So how do you connect this to wave-particle duality? That is the concept of our discussion. So earlier wave-particle duality applied to light. Now de Broglie extended it to matter. This means that wave-particle duality is not just for light. It is for universal property of nature. So the strong takeaway is that if light can behave like matter, then matter can behave like waves. This single idea changed the foundation of quantum physics. Right? Now I want to let you know about electrons in atoms. If you see in this diagram, before the diagram, let me explain you that there is one serious problem in physics. That is what is shown in this picture. In this picture, if you see, there is an atom. At the center is the nucleus. Around it, an electron is moving in circular path. This looks simple, but this picture created a huge crisis. According to classical physics, any charged particle that is accelerating must emit energy. An electron moving in a circle is always accelerating. There is a big problem here. Classical theory predicted this. The electron should continuously lose energy by emitting photons. As it loses energy, it should spiral inward, and finally it should fall into the nucleus. But that does not happen. Atoms are stable. Electrons do not collapse into the nucleus. Matter exists. You exist. So something was clearly wrong. Why this was a shock? According to classical physics, atoms should destroy themselves in fraction of a second. But they don't. This contradiction shows that classical physics has reached its limit. So again, I am connecting these two waves. Now remember de Broglie's idea. Electrons are not just particles, they also behave like waves. This changes everything. So if electrons behave like waves, they do not orbit like tiny planets. Instead, they form standing waves around the nucleus. Standing waves do not lose energy, they are stable. So why only certain orbits exist? Only those electrons waves that fit perfectly around the nucleus can exist. So this explains why electrons have fixed energy levels. So I want to tell you from this image that electrons do not crash into the nucleus because they are not tiny balls. They are quantum waves. And atoms are stable because of wave-particle duality. So the electron as a wave, if you take this idea, right, then you please remember the problem. Classical physics could not explain why electrons do not fall into the nucleus. De Broglie gave us a new way to think, right? So when it comes to de Broglie's idea, I'm showing you this idea in this slide. It suggested that electron behaves like a wave while moving around the nucleus. So instead of imagining an electron as a tiny particle going in a circle, we imagine a wave wrapped around the atom. We imagine a wave wrapped around the atom. So if you see the picture, the circular paths represent possible orbits. The wavelengths represent the electron wave, right? So for an orbit to be stable, the electron wave must fit perfectly. This means only a whole number of wavelengths can fit around the circular path. So if the wave does not join smoothly, it will cancel itself. So on a whole, if you see, when a whole number of waves fits exactly, a standing wave is formed. Standing waves are stable. This is why these orbits exist. Now here a question arises. Why electrons cannot exist between orbits? Now between the orbits, in those regions, a whole number of wavelengths cannot fit. So standing wave cannot form. That is why electrons cannot exist between these orbits. So if you see here, I want to tell you that energy levels appear naturally. Each allowed orbit corresponds to a specific wavelength, and each wavelength corresponds to a specific energy. This is why atoms have discrete energy levels. So these energy levels are not assumed, they arise naturally from the wave nature of electrons. So for the diagram, if you see, electrons do not choose orbits, only orbits that allow standing electron waves can exist. Now we are going to understand about de Broglie's wavelength. Let us understand it in the simplest way. There is no heavy mathematics, no complicated physics, just a clear idea that actually makes sense for you all. Before 1924, it is believed that light behaves like a wave, while matter behaves like particles. So then a young physicist named de Broglie asked a brilliant question. He said, if light, which we thought only was only a wave, can behave like particle, then why can't particles behave like waves? So that question is the opening door to quantum mechanics. So de Broglie proposed that every moving particle has a wave nature. This wave is now called the de Broglie wave. If I want to give you the mathematics, because without mathematics we cannot travel in this entire 100 episode journey, I'll give you a simple equation. Lambda equals to h divided by mv. So how wave like the particle is? The letter h is Planck's constant, a fixed number from nature that appears everywhere in quantum physics. And the term mv means mass multiplied by velocity, which we call as momentum. The most important idea here is this. Wavelength is inversely proportional to the momentum. So when momentum increases, the wavelength decreases. When momentum decreases, the wavelength increases. Think of this as a moving car. Yes, even a car has wavelength, but its mass is too large that its wavelength becomes unbelievably tiny. Unbelievably tiny. That is why we never observe wave behavior for every object, everyday objects. Now think about an electron. An electron has extremely small mass and moves very fast. Because of this, its wavelength becomes large enough to be measured. That is why electrons clearly show wave behavior, especially inside atoms. So this equation which you are seeing applies to everything in the universe, electrons, photons, humans, even planets. But wave behavior is noticeably only for very small particles like electrons. And this idea is extremely important because it explains why electrons don't crash into the nucleus, why atoms have fixed energy levels, and how quantum mechanics works. So in fact, modern technologies like semiconductors and quantum computer exist because of this concept. So if I want to tell you in single line what is de Broglie idea, every moving particle has a wavelength, but wave behavior is noticeably only for tiny particles. Right? So that is what I wanted to tell you. So if you see here, I want to tell you about electron diffraction. Diffraction is something we normally associate with waves. I already spoke about it. For example, when water waves pass through a narrow opening, they spread out. When light passes through a small slit, it bends and spreads. This bending and spreading is called as diffraction, which I already told you. So now think about electrons. If electrons truly have a wavelength, as proposed by de Broglie, then they should also show diffraction when they pass through very small openings or interact with very closely spaced atoms. And that is exactly what happens. So when a beam of electrons is sent towards a tiny crystal, thin crystal or narrow gap, the electrons they spread out and form patterns, just like waves do. And these patterns are called diffraction patterns. Even more interestingly, electrons also show interference. This means that electron waves can overlap with each other. sometimes adding up to form bright regions, and sometimes cancelling out to form dark regions. This is purely a wave-like behavior. So this result was extremely important because it provided experimental proof of de Broglie's idea. It showed that electrons are not just particles, they behave like waves when the conditions are right. So the key idea is that if electrons have a wavelength, they must behave like waves, and diffraction and interference are clear evidence of wave behavior. So when electrons show diffraction and interference, it confirms their wave nature beyond any doubt. So electron diffraction proves that matter can behave like wave, and this discovery became one of the strongest foundation of quantum mechanics. So please remember, electron diffraction is the experimental proof of the wave nature of electrons. Right? So that is what I wanted to explain very clearly. And if you see here in this pictures which I am showing you, right? The image on the left shows something very special. It is the first electron diffraction pattern ever recorded. At first glance, it looks like a set of glowing circular rings. But these rings are extremely important because they are clear evidence of wave behavior. See, I will tell you the entire story behind this image. Scientists fired a beam of electrons at a crystal. Now the gaps needed to produce diffraction, and they are incredibly small. So small that they're actually the gaps between atoms inside a crystal lattice. So when electrons passed through these atomic gaps, they didn't behave like tiny bullets. Instead, they spread out and formed a diffraction pattern, just like waves do. So those circular regions are exactly what we expect from waves undergoing diffraction and interference. So this was the moment when the wave nature of electrons was no longer just a theory, it was experimentally proven. So once this wave nature of electrons was firmly established, it led to something revolutionary. It allowed scientists to build electron microscopes. Now you see the next image, second image. This is a highly magnified image of tiny organism captured using an electron microscope. So ordinary light microscopes cannot see details this small because the wavelength of light is too large. But electrons have a much smaller wavelength. Because of their wave nature and very small wavelength, electrons can reveal extremely fine details, far beyond what light can show. So electron microscopes use this wave nature of electrons to produce incredibly sharp and detailed images of atoms, cells, and microscopic structures. So the same concept that started as a simple question, do electrons behave like waves, ended up changing science and technology forever. Electron diffraction proved the wave nature of electrons, and that proof gave us tools to see the invisible world. If I want to simplify the things, electron diffraction is not just a physics experiment, it is the foundation behind one of the most powerful imaging technologies ever created. And finally, I want to show you these images, right? They show the real power of electron diffraction and the wave nature of electrons. If you see these pictures, they look like something from another planet, but these are not artistic diagrams. These are real images captured using electron microscopes. If you see the image on the top left shows tiny pollen grains or microscopic particles. Even each of these objects is far smaller than what any light microscope can clearly see. The level of detail here is incredible. The textures, the shapes, even the tiny surface structures. The image on the top right shows hair-like structure at a microscopic scale. These could be tiny fibers, surface structures, biological components. What's amazing is that each thin strand you see here is far smaller than the wavelength of visible light. Now you see the image at the bottom. Notice the scale bar, that is 200 nanometers. That's 200 billionths of a meter. At this scale, we are literally looking at structure made up of thousands or even hundreds of atoms. So how this is possible? The answer lies in the wave nature of electrons. Because electrons have a small wavelength, much smaller than visible light, they can resolve extremely tiny details. When electron waves interact with the surface of a material, they scatter, diffract, and interfere. This scattered information is then collected and converted into an image. If I simplify the things, electron microscopes use electrons as waves, not just as particles. The diffraction and interference of electron waves allows us to see structures that lights can never reveal. So this is a direct, powerful application of de Broglie's idea. So if you see, the question was, do electrons behave like waves? And it ended up giving humanity the ability to observe viruses, cells, nanomaterials, and atomic scale structures. So every image you see here is not just a picture, it is a proof that electrons behave like waves, and that wave behavior could be used to explore the smallest details of our universe. So that's the beauty of quantum physics. An abstract idea turns into real technology, and that lets us see the invisible. If you are enjoying this journey from theory to real world applications, do like this video, subscribe to my channel. In the next video, I will go as per the outline I have shown at the beginning. And I hope you enjoyed this video. Do provide your valuable questions. It took me a lot of time to make this video, and a lot of efforts went in. With your appreciation and valuable comments, I will continue my journey, and I will complete this entire quantum computing journey in a 100 lecture series in the best possible manner, giving you the best possible details. Thank you for your love and affection. Thank you all. Have a great learning. Bye bye.